Today I am going to discuss the new topic of nanomaterials, which is very much interesting and rather very important for considering the nanomaterials as today's essential component. Okay, so what is the name of today's topic? This is the electrical transport properties of nanomaterial. Okay, nanomaterial. Till now, what we have discussed is the discussion on nanomaterial. What are the nanomaterial? What is the length scale used for discussing the nanomaterial? Okay, and how can we produce the nanomaterials? Different process was there: physical, chemical, biological, out of which the chemical process is important for large scale production, but it is quite hazardous because of the production of waste materials, which is very much harmful to our environment. In this case, the biological method is more suitable, as because in this case the environment friendly components are produced as a byproduct, and it is very much helpful for our green method of preparation. Okay, so physical process is temperature dependence, and it is dependent on the temperature, and it is not more than costly as compared to the chemical process. But for large scale production, chemical process is very useful. So these was the process regarding the synthesis of nanomaterial. Now we have to first know why we should consider the nanomaterial. As I said before, nanomaterials, by reducing the dimension and size of the bulk materials, many interesting properties generated inside it. One of which is electrical transport properties. We will notice that the electrical transport properties is somehow different as seen from the macroscopic object, that is for conductor. In case of nanomaterial, the electrical transport properties is very much different and very much interesting, and we will deal with it in today's discussion. Again, when you study the optical properties regarding the nanomaterial, you will see that the optical properties is also different for case of material in which the material dimension is of the order of nanometer. That is why today nanomaterial is very important material for our discussion. And in this nanotechnology subject, you can see that all the branch of physics is accumulated here. It involves electricity, magnetism. It involves the solid state physics, concept of solid state physics, that is a condensed matter physics. It involves the concept of quantum mechanics, as because nanomaterials are very low dimensional structure, very small microscopic structure, and in the microscopic world quantum mechanics is very much useful. As well as while considering the particle distribution inside the energy levels, you have to consider the statistical mechanics also. So all the branch of physics gets accumulated while discussing the nanotechnology. That is why nanotechnology is a very important branch of physics in modern life. Okay, so without wasting any time, let's back to our discussion, that is the electrical transport property of nanomaterial. Now the two important things that we have to consider here is the single electron transfer and single electron tunneling effect, and the quantum size effect. Quantum size effect. Okay, so scientists were very much eager and gave their effort to make an interplay between these two processes. Now, while discussing these in the quantum sized nanomaterials, many important phenomena have arrived. Now, we have to first know the single electron tunneling effect. In this case, a single electron gets tunneled from one junction to another. Okay, so the single electron tunneling effect means the tunneling of a single electron from which to which we will discuss. And quantum size effect due to the reduced size of the material, bulk material in case of nanomaterials, the quantum mechanical effect gets dominated here. So there lies a huge difference between the conventional devices in the sense of the electronic transport governed by the quantum mechanics for the case of nanomaterial. So if you are asked what is the difference, what is the difference between the electrical transport in case of nanomaterial than the bulk material, the answer is quantum mechanics. Due to the reduced size of the material, quantum mechanical law gets involved in case of the nanomaterial for the electronic transport, and by the application of the quantum mechanics, many interesting properties in case of the resistivity, in case of the conductivity, in case of the uh, potential, energy, etc. order of interesting phenomena you will notice by the application of the quantum mechanical law. Now at first you have to understand the different process of the transportation. Okay, as because the heading involves transport properties, so you have to understand different transport properties involving in case of the nanomaterial. One of the property is parallel transport. Parallel transport, what is it? Okay, if in case of nanomaterial semiconductor, the electrons, that is the conducting materials, that is the uh, particles get involved in the conduction of the electricity, the electron in the conduction band, so I can write that the conduction band electrons in quasi 2D well behave almost as free carrier for their motion along planes parallel to the interface of the well. So if you assume the conduction band to be a infinite square well and valence band to be a infinite square well, and electrons get tunneled from the valence band to the conduction band, then for the case when the conduction electrons are present in the conduction band and it moves in the planes parallel to the interface between the two wells, conduction band wells and valence band wells, when the electrons get moved parallel to the interface between these two wells, Then the movement of the electron or transportation of the electron in this case is known as the parallel transport. While if tunneling occurs from the valence band to the conduction band, then it is called the perpendicular transport. This is known as the perpendicular transport. And perpendicular transport involves quantum mechanical tunneling, as you can see from the figure drawn above. So this is known as the perpendicular transport, whereas uh, the parallel movement or parallel transportation of electron is known as the parallel transport. Okay, so these are the two transportation process involves when a semiconductor nanomaterial is present in our study. Next, when some external voltage or external current source gets added to the semiconducting nanomaterial, then there involves some interesting conduction process which is known as quantum transport or mesoscopic transport. Mesoscopic transport. If you are asked to give the definition, then you can say that mesoscopic transport is produced when the nanostructures are connected to an external current sources by means of leads or contacts. Okay, so these are the three types of transportation process involved in the nanostructure semiconductor, where the first one is parallel transport, second one is perpendicular transport in which the quantum tunneling gets involved, and the last one is quantum transport or mesoscopic transport, which gets involved when the semiconducting nanomaterial is connected to some external current source by means of leads or contacts. Okay, one of the interesting phenomenon which appears in the mesoscopic transport. So one of the interesting methods or one of the interesting phenomenon appears in the quantum transport or mesoscopic transport is that its resistivity or conductance. Sorry, resistivity, not resistivity. It is the conductance. Conductance, which is the reciprocal of resistivity. So conductance is quantized. Quantized in units of e squared upon h with 2 square by h. So you can say that the resistivity is quantized in units of h upon 2 e square. This is quite strange and quite interesting, as this is not seen in our macroscopic materials. Okay, so another interesting property can be shown, which is known as the Coulomb blockade effect, which we will later discuss in detail, which is known as the Coulomb blockade effect. So all of these are present in case of mesoscopic transport. In case of mesoscopic transport or quantum transport, the conductance is quantized in units of 2 squared by h, and there is a Coulomb blockade effect. What is this? We will discuss in later details. Okay, so till now what I have discussed, this is the electrical transport properties of the nanomaterials, where we first give the different transportation process, that is the parallel transport, perpendicular transport, as well as the mesoscopic or quantum transport. And in case of quantum transport, some interesting phenomena gets arises, which are uh, known as the Coulomb blockade effect, and also the conductance, quantization of the conductance and resistivity. Okay, so next we have to discuss what is the different carrier transportation process in the nanostructure. So let us put a heading, sorry, carrier transport process in nanomaterial. Okay, so to discuss the carrier transport process in nanomaterials, I first want to ask you a question, and the answer we will get find in this discussion. So we know very well that in macroscopic case, I is equal V by R as from Ohm's law. We know it very well in case of the macroscopic conductor. Okay. So my question is the same relation may also true in case of the uh, nanostructured conductor or nanostructured material? Nanostructured material, is this also true in the same form as observed in the microscopic material or nanostructured material? This is our main question to find out in this discussion. I will get you the answer in the last of the discussion. So let us first discuss different uh, effects while the transportation of the electron. Effects of electron inside the nanostructure, in nanostructure. The answer will coming out at the end of this discussion. Okay, so till now hold the patience and listen what I tell. So effects of electron in the nanostructure. What kind of effects gets involved in case of nanostructures? We have to point it out first. First thing is very much important, quantum confinement. Due to the reduced dimension and reduced size of the material, the quantum confinement becomes dominant here. Quantum confinement effect. So electrons get trapped inside the material body, and quantum confinement effect becomes dominant here. The second one is, as I show or as I told you before, tunneling effect. Tunneling effect. You know very well from the quantum mechanics. Tunneling effect. Third one is charge discreteness. Charge discreteness or charge quantization is also true in case of the macroscopic body, but here the quantization of conductance gets also involved. So the laws which can hold in the macroscopic scale is also valid for the microscopic scale with some modification. So charge quantization is also, or charge discreteness may also present here, discreteness, and the Coulomb sorry, and the electron Coulombic interaction. Coulomb interaction. fourth one is strong electric field effect. If we apply some strong electric field to the system, what will change? We will see the strong electric field effect. And the last one is ballistic effect, ballistic transport effect. Ballistic transport effect. Which effect will be dominated in which cases? I will give you the conditions now. So, for knowing the conditions that which effect will be dominated in which cases, you have to consider some length scales. You have already studied the Planck's length while at the beginning of the nanomaterial, that is equal to the root over h line g by c cube, where g is a gravitational constant and has the value of which is of the order of 10 to the power minus 11, 6.67 10 to the power minus 11. Okay, so for here also you have to study some length scale. Before studying the length scale, you will not understand what is going to show you, or what are the cases involving the different effects. So there are two length scales important here. The first one is known as the distance average distance traveled by the electron before elastic scattering, or not being elastically scattered, not being elastically scattered. The average distance traveled by the electron inside the conductor, obviously nanostructure material conductor, uh, where the electrons are not being elastically scattered, the average distance is traveled is known as the AD, that is the elastic scattering distance. Okay, elastic mean free length, you can also say E as elastic mean free length, mean free length. Now if I consider the Vf to be the Fermi velocity of the electron and tau e be the relaxation time for the electron, then it must have this obviously this relation should be hold if Vf be the Fermi velocity, tau e be the relaxation time, elastic relaxation time, obviously that is the time taken between the electron to travel LE distance. So Vf into tau e will equal to the LE. Similarly, if there are two electrons and which are going to travel inside the nanostructure material, before the phase difference of the two electron due to traveling being not equal to the same, the distance traveled is known as the phase coherent length. What I say? Average distance traveled by the electron before their phase is randomized is known as the phase coherent length, and the phase coherent length is designated as L phi. And similarly, if we consider the tau phi to be the dephasing time, that is after which the electrons gets uh, different phase difference. Okay, the phase difference will not be constant, the phase difference will change after the time d phi. So d phi is known as the dephasing time, and this was the elastic mean elastic relaxation time, and this is the dephasing time. So this is also true, Vf into tau phi will be equal to some L phi. So these are the two length scales. that is the mean elastic free length, and the phase coherent length L phi. This is known as the, sorry, this is the phase coherent length. Okay, so there are two different uh, length scale parameters. Now we know that if lambda f be the Fermi wavelength of the electron, then this, according to the Louis de Broglie hypothesis, will be equal to h by Fermi momentum. Now again, for d dimension, let us suppose the general case, for d dimensional structure, the number density n will be equal to some n divided by phi d. Phi d is what? In case of 3D, it is the volume term, but here I involve the d-dimensional structure, so phi d depends upon the dimensionality of the uh, space considered here. So in this case, you have to memorize, otherwise you can prove also, but it is some higher physics. The proof is not given to our syllabus, so I am not going to prove you, but you have to remember this. That is a kf, which is the wave vector for Fermi wave vector corresponding to d dimension, the Fermi wave vector corresponding to d dimension, which is equal to 2 pi whole to the power d, 2 into pi to the power d by 2 gamma d by 2 plus 1, also equal to the n, where n is equal to capital N, that is the total number present in the d-dimensional structure, divided by the uh, volume, similar to the volume phi d term. Okay, omega d term. This is similar to the uh, volume term in the 3D. In 3D we can get the number density as n by v, but in case of d dimension you can get this. So here you can find that kf for two dimensional, this is not the square, this is for two dimension. So two dimensional case, if we assume the two dimensional case, then it will be 2. If you put the value of 2, then put the value of 2, then it will pi. So there will be pi and 2, here 2 square, so 2 will get here, and gamma 2 means 1 factorial, so the only term gets survived here is, for two dimension, the Fermi wave vector is nothing but 2 pi n. This will be used later. Okay, now let us point it out the different conditions for the different effects to be shown by the electron inside the nanostructure, that I have already mentioned at the right hand side of this page. That is a quantum confinement, tunneling effect, ballistic transport effect, etc. So when the dimension of the nanostructure material, if we assume these to be equal to L, when the dimension of the nanostructure material, which is equal to the dimension of nanostructured material, this is, if L be less than equal to some LE. What is LE? Elastic mean free length. Then the effect which gets dominated is ballistic transport effect. Ballistic transport effect. Next one, if the dimension of nanostructure material be less than fetch coherent length, then it will be fetch coherence. Show fetch coherence. Fetch coherence effect. The next one, if the dimension of L be less than Fermi wavelength associated to the electron, then this will give you the size quantization. Size quantization effect. And lastly, if the thermal energy corresponding to the temperature T be less than E square by C, then it is the condition for single electron transistor, in which the transportation of only one electron gets involved. Single electron transmission may also say. Now this statement will be proved soon. This statement will be proved later. Something went wrong here. Please give me some time. I think this is software issue. Okay. So let us back to the discussion where we have left. Okay. So the single electron transistor we will say, we will discuss in the later. But I first give you the question at the beginning of this discussion, that the law which we will know in case of the macroscopic material, which is the Ohm's law, can it be true in case of the microscopic material, that is the nanostructure material, also in the same form? The answer is discussed now. So by the considering LE, you know that this is the average distance traveled by the electron before elastically scattered, before it elastically scattered. Okay. Now the statement, or to give the explanation regarding the nature of the Ohm's law in case of the nanostructure material, we have to consider the Drude's theory of conductivity. Okay, Drude's theory of conductivity. So let's consider random collision process of electron. Okay, random collision process between the electrons. So the electron taken random at time t will have a collision before time t plus dt. This is a small interval. So that the electron taken random at any time t will have a collision before the time t plus dt has the probability sorry has the probability which is equal to some dt upon the tau e, where tau e is the elastic relaxation time. So it is the probability for the elastical scattering of electron within the time interval t and t plus dt is dt by tau e. So in another words, we can say that the probability that the selected electron in the time t will not have any collision before the time t plus dt will have the probability 1 minus dt upon tue, as because the total probability of getting collision or not is equal to 1. So if the probability to get the collision within the time interval dt be dt by tau e, then the probability for not getting a collision will be 1 minus upon this. Thus, according to the joint probability of independent process, the collision probability at t plus dt time interval will satisfy the equation pt plus dt will be equal to some pt into 1 minus dt by tau e. Now if I am going to normalize the pt, then I will get pt to be equal to e to the power minus t by tau e divided by tau e. 0 to tau e, if we integrate the pt function, then we will equal to the function to be 1 according to normalization of probability that we have discussed in the probability lecture at the beginning of the statistical mechanics. So we can say that the pt will have to be equal to e to the power minus t by tau e by tau e. Now again we know that uh, the velocity at any instant of time t of the electron will have to be equal to f by m into t. Now if the electron is acting by the electric field E, then it will have the value E by m into t. So V at tau e will be equal to E tau e divided by m. Now again current density is known to be equal to J is n E into V, where n is the number density, E is the charge of electron, V is the drift velocity or the velocity attained between the two successive collision. So if I put the value of V tau e in case of this, then we will get n squared tau e divided by m into some E, this E. Why I am separating this term from E? As because you know from the differential form of Ohm's law, J is equal sigma E. So you by comparing these to be equal to this two relation, we can say sigma will be equal to n squared tau e upon m. Now, what is the value of tau e? As I have discussed sometimes before. Yes, from this you can easily say that tau is nothing but mean coherent length, mean elastic length, mean elastic free length divided by Vf, Fermi velocity. So by putting the value of tau e here in E square L E divided by what I say Vf. Now again MVF, okay. MVF means PF and PF means H line KF. Okay, some step jumps I have used. So this is equal to this into LE. Now I have multiplied KF at the numerator, so I have to multiply also KF at the denominator, and we will get the result like this. Now I separate out each term by the process here. E square upon H line, which is the constant terms, n upon kf square and also kf LE. Now it has seen from the different experiment, if we assume this to be equal to 1 and kf square for 2 dimension, if we assume the case for 2 dimension, then kf square means this kf in 2 dimension. Okay, so this is also kf square. The dimension means the power of the system. I have said before that this is not the power, but I was wrong. The dimension also gets involved to the power of the kf as seen from this calculation. Okay, so sorry for the wrong statement, but here you can easily see that kf square means the two-dimensional uh, Fermi wave vector. So by applying the value, you will get 2 pi n. So n gets cancelled out and we will get only 1 by 2 pi e square upon h. And h line into 2 pi means h. And the term within the bracket is taken to be equal to 1. If we take this, then this will be e square upon h line. So you can also, if this is not 1, then you can take also this. It may have some value, but the thing which is important here is the conductivity is of the unit of e square by h. This may have some value 1, 2 or other kind of value, but the term gets involved here is e square upon h. So we can say that sigma is not at all a constant. This is a rather discrete quantity, which the discretization constant to be e square upon h. Similarly, you can say that resistivity is also equal to h upon e square in units of this. So quantized with the quantization of h upon e square. So the statement, as I said before, that the conductivity and the resistivity is quantized. Okay, so the conductivity is quantized of the order of 2 e square by h, and the resistivity is by 2 e square. So from here you can say easily like this. In general, resistance of such randomized material can be expressed as RL to be equal to h by 2 e square exponential to 2L by LE. Now this is a long derivation. If I am going to prove it, then it will take a long time, and the total proof is not present in our syllabus. So if you want to show this proof, you can refer to any book regarding the higher physics, so that you will understand better the how can the resistance arrive. But the important thing is that the resistance is not at all a constant, but it also depends on the dimension with the exponential. Okay, so the additive law of resistance is not followed here. That is, the superposition principle is not followed here, as because the resistance is not at all dependent linearly with the length of the nanomaterial linearly, but it depends with the exponential of the length of the nanomaterial size involved. So some interesting properties. It is very much interesting as you have observed from this. There is another interesting properties regarding the nanostructure material, which is the Coulomb blockade effect, which we will be discussed in the next lecture. But what uh, I have discussed till now, if I am going to summarize, then you can find out differences between differences 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 of conduction at nanoscale and macroscale and nanoscale. Now from the size you can say that the different many large number of carriers gets involved in case of the macroscale object, whereas nanoscale objects gets involved only a small fraction of carrier, electrical carrier, as because this has the structure very small, so the number of carriers such as electrons or holes will also be very small. But the interesting fact is that in case of the nanoscale, a very small fraction of the carrier waves can generate a huge interesting phenomena or huge drastical change in the nanoscale device of the electrical behavior. Now the resistivity as seen from the normal conductor, that is a macroscopic conductor, is seen to be vary linearly with the length, but here the resistivity is not at all linearly. You can linearly vary it. You can see it from the expression put it in a box, that RL is the function of the exponential to the length of the dimension. So this is not at all a fixed additive property. This will not follow the additive property of resistance. Suppose the resistivity of, and if the law is not followed by resistance, this resistivity will not be followed. So if the length of the resistance length of the material be increased by 2 times, then for macroscopic object you can say this, but for nanoscale object this will not be equal. So the additive law is not followed here. Okay, as because it involves some exponential term. Now the quantum effects are averaged out by the thermal effects in case of the macroscopic condition, but the quantum effects gets dominated in the nanoscale condition. And because of the nanoscale dimension, the effective capacitance is very small, as because we know that the capacitance is directly related to the area. For parallel plate capacitor, you know that K epsilon naught E upon D. This is so area, the capacitance is related to the area, so smaller area will involve smaller capacitance, so the capacitance of the nanostructure material is very small. That is why the electrostatic energy is also small as compared to the macroscopic object, and the resistivity is quantized in the nanoscale as seen from this above expression, which is not true for the macroscale object. So thank you very much. These are the all discussions for the different interesting phenomena involving the electrical transportation of nanomaterial. Okay. So in the next few lectures we will discuss the Coulomb blockade effect, single electron transistor, and the other interesting electrical phenomena in detail. Thank you very much till now. Please wait, and if you enjoyed, then press the like button and subscribe the channel for more updates. I have very much working hard to grow up this type of video, so if you enjoyed, then it will be very uh, happy thing to me. Thank you.